I forgot to record. Oh no, we're good. We're recording. Okay. I forgot to record last block. Okay, so what we need to consider here is that our x-axis is where the kinetic energy goes. Now, this is different. If you remember last week, we were doing potential energy diagrams. Where did the potential energy go? It went on the y-axis. So tomorrow, we're actually going to put these two kind of together a little bit, but not today, okay? The kinetic energy is going along the x-axis, and along the y-axis, we have the number of particles. So at a very high temperature, or sorry, at a very high kinetic energy over here, what does that tell you about the particles? They are moving very fast. And how many molecules do we actually have that are moving super, super fast? Not very many, yes? We have a much larger amount that are kind of moving at a medium kinetic energy, yeah? And again, a fairly small amount that are moving very slowly, in other words, at a low kinetic energy, all right? For the purposes of grade 12, we're going to say that this peak here is the average kinetic energy. So if we were to go all the way down here, we would say that that is the average kinetic energy of all the particles. Technically, that's not really the average, but for grade 12, it will do. Now, how many of you have seen a bell curve that looks like this? Anyone seen a bell curve? Maybe in statistics or just in math or something like that. That's a bell curve. We have a similar shape to a bell curve, but not quite. Because you'll notice that at this end over here, it doesn't go down like a bell. It goes chunk down to 0. And that's because no particles have 0 kinetic energy. Okay, that would mean that they were not moving at all. How many of you are familiar with the idea of an asymptote? Yes? Yes. You don't need to know much about it. Okay, you just need to know that on the other side of the curve, the curve approaches the x-axis asymptotically. Asymptotically. Like an asymptote. In other words, you are not going to have to use that word. You can just say it gets closer and closer to the y-axis, or sorry, the x-axis without actually touching. So on the left-hand side, we go chunk down to 0. On the right-hand side, we have this tail. That's not an official name. I'm just going to call it the right-hand tail because it trails off there. Okay? How are we feeling about the basic shape of the curve? Decently? Okay. What is the area under the curve? Yeah. The area under the curve is the total number of molecules. And just in case I haven't told you yet, MC means molecule. Okay, so this is called a kinetic energy curve, a kinetic energy diagram. When you go to university, they might call it a Maxwell-Boltzmann distribution. The only reason I have that in here is that my AP Chem class uses this same book. So there we are. You don't need to know it. All right, so we know that the total area under the curve represents the total number of molecules, and the peak represents the most probable kinetic energy. In other words, the average kinetic energy, at least one type of average. Which one is the most probable? Is that the mode? I think it's the mode. Or is it the median? It's the mode. Yeah. Anyway, we're going to call it the average kinetic energy. All right. So, activation energy, we did hear about this last week. Activation energy is the minimum amount of energy with which particles must collide. It's the minimum amount of energy needed for particles to react. And that's just different for every reaction. It just depends on the nature of the reactants, okay? Now, it also says here the minimum amount of energy with which particles must collide in order to be able to form an activated complex. We will talk about activated complexes later today. Today, we're just going to ignore the fact that that is there, okay? Now, here is a reaction. Here is our activation energy, which we can abbreviate as EA, okay? So this is the minimum energy needed to react. And all of these little molecules in this section of the curve will react because they have enough energy. Okay? However, molecules with this amount of energy, so anything here and below, they will not react because they do not have enough energy. Now, if you had to guess what fraction that is. What fraction is the green of the entire curve? Have a little chat with your neighbor and decide what fraction of all the molecules actually have enough energy to react. I don't expect a good estimate, just make any ballpark estimate you can. Of course. Yeah. Yes. Yes. We are just saying, yeah, let's just assume they have correct alignment. What's going to happen is that statistically, there will be as many collisions in that area that have the correct alignment as in the other area that have the correct alignment, so we can just kind of ignore it. Yeah. Good question, though. Okay, what do we think? Any numbers you want to throw out at me? 1/8 could be an eighth. Any other numbers? Could be 1/7. Yeah. We're just kind of guessing, right? So I think I guessed 1/10. Okay, but it really doesn't matter. I don't know, my whole other class wanted it to be 1/20th. Somebody said 1/20th, and then I'm like, anyone else got another number for me? And then someone was like 1/19th. And then another person was like 1/21st. I was like, well, those really seem like, I don't know if it seems like that to you, but those seem like really small fractions. But regardless, it doesn't matter really which number we pick. I'm going to pick 1/10 just because that way I can say 10%, because that makes my life really nice and easy, okay? Let's just say 10% will have sufficient energy to react, okay? Now, the actual number is not important. You will not be asked to do that estimation on a test or quiz. You will not be asked to do this on a test or quiz. It's more of a little mental exercise for now, okay? Okay, here's a different reaction. And now our activation energy is much higher or lower? Lower. Yes, because this is high kinetic energy over here. This is low kinetic energy over here. So we have a much smaller activation energy. And what can you say about that green section of the curve? All of these have enough energy to react. So approximately what fraction is that? I heard a 5/6. Any others? 6/7, sure. Okay, at any rate, it's greater than 50%. Yes? Greater than 50%. And we really don't care. All we need to know is that when the activation, we need to know the relationship between activation energy and the percent of collisions which will be successful. So what I would like you to do is I would like you to make a sentence relating these two things. So I would like you to write a sentence relating activation energy and the percent of collisions which will be successful. See if you can write a cohesive sentence. And once you've written a sentence, check with your partner, see how yours compares to theirs. What could I put in those blanks? The lower, okay. The lower the activation energy, the greater the percent of what? Collisions, which will be successful. Is good? Okay. So that's the diagram, and that's how it relates to activation energy. Now we're going to look at the diagram and see what happens when we change the temperature. Oh, I'm moving too fast. Sorry. Okay. Okay, so temperature. Tell your partner, what does the word temperature mean? What is temperature?
Average kinetic energy.
So temperature is a measure of the average. The average what? Kinetic energy of the particles. Good. So if we increase temperature, what have we done to the kinetic energy? We have increased it. So if we increase temperature, we have increased average kinetic energy. Whoops. So let's go and look at our average kinetic energy. Let's go back. Oh, there we go. There is our average kinetic energy. Where is the average kinetic energy? It is at the peak. I meant to highlight that, but a circle will do. Okay. The average kinetic energy is at the peak. So if we have increased the temperature, what will happen to the peak? It will move. Which direction will it move? Will it move to the left or to the right? To the right, because it's moving to a higher kinetic energy. Okay. So, as temperature increases, the average kinetic energy increases, and the peak, which is the average kinetic energy, will move to the right, in other words, to a higher kinetic energy. I think it should be obvious, hopefully, that as we make the average kinetic energy higher, there will be fewer slow molecules. Yes, and there will be more faster molecules. What about the very fastest molecules? Fastest molecules at the lower temperature, will they be the same fastness as the fastest molecules at the higher temperature? That's a terrible sentence. I'm sorry about that. Which one will have the fastest molecules? Higher temperature, okay? So the fastest molecules are going to be faster than they were before. So in other words, we're going to take, if this is our low temperature, the blue curve, okay, that's our low temperature. And here we have the fastest molecules at the low temperature. We can compare that with the fastest molecules at the high temperature. Yes. Yeah, we'll talk about why in just a second. I should just say high, not highest. So we have our average kinetic energy at the low temp. Okay. And then our highest temperature curve is the red one. This is our average kinetic energy at the high temperature. So the peak has moved from the left to the right because the average kinetic energy at the high temperature is higher. Shocking. When we increase the temperature, what happens to the total number of molecules? They stay the same. They're just moving faster. What do we know about the total number of molecules? It stays the same, but do we know anything about that curve and the total number of molecules? What does it equal? The area under the curve. So in essence, what we've done is we have made, as we get to a higher temperature, the entire curve gets wider. Yes? What has to happen for the area to stay the same? It has to get shorter. Yes? So if the entire curve gets wider at the higher temperature, where can I write this? Over here. For the area under the curve to stay the same, the curve needs to get shorter. So why must the peak get lower at higher temperatures? Well, if we look at this area of this little box here, we have a 4x3 box, right? And the area is equal to 12, yes? If we make that box wider, right? And now we have a 2x6. In order for this to get wider, the height has to get shorter in order for these two to remain equal. Yes? So that's why the curve sort of flattens out as we go from a higher temperature to from a lower temperature to a higher temperature. So in summary, when the temperature is increased, what happens to the peak? Two things happen to the peak. The peak moves to the right and the peak gets lower. In other words, the curve flattens, gets shorter. And the other thing that happens is that the curve gets wider. And then vice versa when temperature is lowered. Yes? Yes, I sure could. And go up a bit. How's that? Okay. Is it too small? Okay. You guys have better eyes than I do. Yeah, and I can tell people at the back of the room are like, what does it say here? I'm just gonna like, yeah? Do you want to move closer, Cher? You're okay? Alrighty. Oh, here's a little trick for people who have glasses. If you would like your glasses prescription to be a little bit stronger, you take them and you tilt them a little bit. So you can find the angle that makes them the best. It doesn't work for me anymore because I have progressive lenses. This is the part I read with, but you can do that. Back in the day before they had like fast glasses making abilities, back when I was a kid, that was how I spent 6 weeks in my class, was sitting there in grade 5 like this, so I could see the board. Okay, we good? And don't forget, if you ever want to check out these notes, where can you go? You can go to Teams. Oh my gosh, look, here we are. And you can go to the main channels and go to class notes and click on that. And hopefully everything will pop up. So you can say, oh, okay, we were doing kinetic energy diagrams. Oh, there we are. And everything is there for you. So if you want to go home and you're like, I didn't quite catch everything, you can be like, ah, that's what it said. Okay. All right, let's get rid of that. Now, come on, let's behave. Why are you not scrolling? Oh, it's thinking hard. Okay. There we go. All right, so here we can look at a kinetic energy diagram can be used to explain why an increase in temperature affects the rate. So an increase in temperature affects the rate. So here we have a certain fraction. Yes, I don't know. I would guess this is about 1/5. I'm just totally making up that number. I don't know if it is 1/5 that have sufficient energy to react. But all of a sudden, if we heat it up, the activation energy stays the same. Yes? The activation energy stays the same. And you can see that the area under the red curve is a much higher fraction. I might say that that's 1/3 or something like that. Is that making sense? Okay. So that's why temperature affects the fraction of collisions with sufficient energy. How about catalysts? Sorry, you have a question. Stays the same. Oh, except for like somehow the became a T and just went in the middle of the word. Stays the same. You can tell it's the end of the day. Whoa. Huh. Thank you. I was like, there's a puzzlement on that face. I see it. I see it. Okay, now, what is a catalyst? We don't know a lot about catalysts yet, but what we do know is that a catalyst does what? Lowers the activation energy. Okay, so here is our activation energy with no catalyst. And here's the activation energy with catalyst. Does the catalyst change the energy of the particles at all? No. You can see the curve remains the same. The only thing that's changing is that activation barrier. We start with no catalyst is over here, yeah? And then with the catalyst is everything there, okay? And I'm not even going to give a fraction. I'm just going to say what fraction? A smaller fraction have sufficient energy without the catalyst. And what fraction with the catalyst? A greater fraction. Okie dokie. And let's see, is that it? That is it. How did the questions go? How did you guys feel about the questions? Yeah? Would we like a 5-minute break before we carry on with potential energy? Okay, stretch break, 5 minutes. You can go and get water. You can go to the washroom. We'll start at 35, actually 36, according to that clock. But I think that clock might be a little bit fast or slow or something. I don't know. Oh. Yeah. Your test, I think it's going to be next Wednesday. Okay? The 21st. We will have another quiz beforehand. Oh, yeah. So I feel like we might have a quiz this Thursday. Oh, I'm so sorry. And then you can get it back on the Tuesday, test on Wednesday. Yeah. Hi. Huh? The quiz on Thursday? Oh, it'll be on everything. Woo.
Whoa, what do you mean close?
It'll be on all of that. 1.3 to 1.5.
We're coming 1.4.
Yeah. All three. Yeah. We might not get through everything. Test might have to be a little bit later, but we'll see. We'll see how we do. It can't be on Thursday. What's on Thursday?
I have 2 other tests.
Oh, well then let's not put it on Thursday. We can't put it on Friday. Wednesday?
Okay.
Okay.
Wait, which Wednesday?
The 21st. Not this Wednesday, but next Wednesday.
Oh.
Yeah?
I mean, I have a problem with that.
Yeah, let's do it next Wednesday.
No.
It's better for me too, because otherwise I have everybody, all of my classes writing tests all on the same day, which means I have to take them all home and mark them all. But to be honest, it's not like I'm going to get them marked before the weekend anyway, so. I'll get part way through, but not all the way through.
How does it work? They pay garbage. Okay, what's the good because being gardens? Okay, this section is actually garbage. There's not actually so it's what was worth getting before. Yeah. Okay.
Or lose. Can you lose? Can you lose yardage? There you go. Yeah.
I don't know. know what? You listen to everything. When we go to the bottom, there's 4 trucks.
I mean, like last yesterday,
I heard that, but listen, what
Are
happened?
you feverish?
You got your somebody?
Oh.
Not why.
I have staff. I also have
Yeah.
You know what we could do? We could make the test the following week. Like after? No, you want it next week?
Oh, why?
Friday's shorter day.
Wait, what day is it?
Pardon me?
What day is it?
Wednesday, next week. Okay, bonds and enthalpy. This is page 61. Okay, imagine you are holding a pencil or what is this? A skewer. This is a skewer. If you want to break the skewer, do you have to put in energy or will you get out energy? You have to put in energy. So is that endothermic or is that exothermic? Endothermic, because you had to put in energy. So, moral of the story, we had to break some bonds for that to happen. Bond breaking is always endothermic, and bond forming is always exothermic. So, we are going to expand upon our potential energy diagrams. We're going back to potential energy. In a chemical reaction, you can imagine that you are breaking all the bonds in the reactants, which requires energy to go in. And we are forming all the bonds in the products, which means that energy is going to come out. So we break all the bonds, and then we form new bonds. Break all the bonds, form new bonds. Energy in, energy out. Energy in, energy out. Whichever one is more will determine if the overall reaction is endo or exothermic. Okay? So if we need more energy to break the bonds, then we're going to be endothermic. If we need less energy to break the bonds, that means we get more energy out. Less energy to break the bonds, then we're going to be exothermic. So here is a lovely little picture. We have methane and oxygen. And you can imagine that we go and we break all the bonds. What do we end up with? We end up with individual atoms. Laura, could you shut the door for us? They're being noisy out there. Thank you so much. So we have those individual atoms, and what happened to the energy? What happened to the potential energy as we broke those bonds? potential energy is going this way. Did potential energy increase or decrease? We went from here to here. Potential energy increased. So these guys up here, they are less stable. They're high potential energy. Now, all those individual atoms, they're going to get together in a different arrangement. We're going to now form some bonds here, 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 here. We're making the new bonds, and that's giving off energy. So what's happening to the potential energy now? The potential energy decreases. So now we are at a lower potential energy. And these things are more stable. Is this an endothermic or an exothermic reaction? Tell your partner what you think. Endo or exothermic? We start higher, we finish lower, so that would be exothermic. So our graph, the graph that we would have drawn last week would have looked like this, yes? However, that doesn't tell the whole story, because here we have our reactants, here we have our product, but there's something happening in the middle, yes? And so the energy actually goes up in between the reactants and the products. So instead, what we're going to be looking at from now on is a graph that looks like this, with that peak in it. Does that peak look familiar? That is the activation energy peak. So, and if you remember, this quantity right here is the activation energy. Okay, that's the energy required to break those bonds. So in grade 12, we're no longer going to draw our diagrams like this one here. No longer. Now we're going to draw them like these ones. Okay? So you can see here is an exothermic reaction. Here is an endothermic reaction. And what you'll notice is that in the exothermic reaction, the bond breaking has a smaller amount of energy change, and the bond formation has a greater energy change. The opposite is true of endothermic. Bonds broken, that's going to be the endothermic process. When we have bonds being made, that's the exothermic process. What would we label this arrow here. What would that be called? That is that is our activation energy. Okay, so that's our activation energy. Starts at the reactants, finishes at the top of the peak. Okay? So if we wanted to label our activation energy on the endothermic curve, where would we start? We would start here, okay, at the reactants level, and we would go up to the top of the peak, and that would be our activation energy. Is there anything else we could label on this diagram, maybe that we labeled last day on our energy curves, potential energy diagrams? We could label our axis, so we have our potential energy. This says course of the reaction. That is the same as the reaction proceeds. But there's another arrow on here that we could label. We could label the change in enthalpy. And what's the symbol for change in enthalpy? Delta H. And where is delta H? Where the arrow is. So this here is delta H, and this one here is delta H. Where would the heat term go in this exothermic reaction? Would it go in the reactants or would it go in the products? Products. Is delta H positive or is delta H negative? Delta H is negative. Down here, we would have reactants plus heat gives products. So the heat goes in the reactant side, and delta H is positive. So I don't know why I have a second set of diagrams down here, except for that I made such a mess of these ones. Maybe it's kind of nice to have a tidy one, okay? Oh, and that's it for that. So we're going to go over here to page 63. And this is another perspective on the potential energy diagram. Here we have a reactant particle and another reactant particle. And they are busy looking at each other. Yes? Okay, so they're looking at each other. What do they see when they look at the surface? They see the electrons. Okay? When two reactant molecules approach each other, they see, of course they don't actually see, each other's electron cloud. So we have a negatively charged cloud over here. We have a negatively charged cloud over here. What does negative do to negative? Repels. So I want you to think, as these two come together, they are repelling one another. Have you ever tried to put two north poles of a magnet together? What does it feel like? Is it a stable state or an unstable state? It's unstable. It won't stay there unless you hold them, right? And the moment you let go, whoop, the one will flip around until it's backwards, right? And now it's stable. So likewise, when we have negative repelling negative, the closer they get, the less stable they become, okay? What's another way of saying less stable? You could say unstable, yes. I was thinking of some different words entirely. Yeah, higher potential energy. So the other thing that's happening, this negative is repelling this negative. The particles are approaching each other. Maybe they're approaching at great speed. What's going to happen as they come closer and that repulsion starts to repel? Are they going to keep going the same speed? No, what's going to happen as that pushing apart force starts to come into play? They're going to slow down. Yes, because there's a force acting in opposition to their motion. So as a result of this repulsion, they slow down. In other words, their kinetic energy decreases. Guess what's happening? We started with high kinetic energy. Dear God. And now it's becoming lower. We started with low potential energy and now it's becoming higher. So guess what? Kinetic energy is being transformed into potential energy, right? The kinetic energy gets lower. And the potential energy increases. What's happening to the total amount of energy? The total amount of energy stays the same. That's the law of conservation of energy. So this is what happens when particles approach each other. Now, eventually, if they have enough kinetic energy, they're going to collide. If they collide successfully, what will happen to all those bonds? The bonds will break. Okay, so if we have the correct alignment the correct orientation or correct geometry. And if we have sufficient kinetic energy, we need that sufficient energy to overcome the repulsive forces and to also break the bonds of the reactants. Then we're going to form this thing called the activated complex. And I'm going to break down this definition into 3 parts. Part 1, what is it? It is a chemical species. What is a chemical species? A chemical species is a chemical thing. But thing is not a very scientific word, so we will say chemical species. Okay? Another way of saying it, you could say that it is an arrangement of atoms. So that's the first thing. We need to say, what is an activated complex? It's a chemical species. It's a chemical thing. What are its properties? What are its characteristics? Well, first of all, is it stable or is it unstable? It is unstable. Remember, we've just broken all those bonds. Is it high potential energy or low potential energy? High potential energy. And because it is unstable and high potential energy, does it last for a long time or for a short time? Short time. So we're going to say it is short-lived. Okay, so those are its characteristics. And then finally, we're going to say, when does it occur? It occurs when there is a successful collision. So when you have a successful collision, that's when you get the activated complex. We are very quickly running out of time. I really want to look at the pictures on the next page, and then I'm going to give you your homework. I'll just put it up on Teams, okay? So here's our picture of these reactant particles approaching each other. We've got H2 plus 2H2 plus O2. And then a collision forms, the activated complex forms. But to be honest, this thing is so unstable, right? This activated complex is so unstable, it is so short-lived that we cannot actually isolate it or study it or look at it or do anything meaningful with it. So do we actually know what it looks like? No. Okay? It's like freaking elephants out there. Okay. We don't actually know what it looks like. So what we'll often do is we will represent it as, we'll say, oh, what do I have in there? I've got 4 H's. I've got 2 O's. I just kind of smush all the atoms together. And then I say, well, I don't really know what it looks like, but I do know that it has a lot of energy. And that's what that little star means. We don't actually know what it looks like, but we do know that it has a lot of potential energy. Okay, and the bell is going to go in like a minute. So like I said, I will put the homework up on Teams. I think it's going to be another Mr. Colger video. Hopefully you guys are okay with that. It'll go through this stuff so that you have a preview of it so we can just zoom through it tomorrow. Okay? Excellent. Whew. What's that? More Tyler DeWitt. Tyler abandons us for most of Chem 12 and then only really comes back in the last unit. But he comes back strong. Okay, I know. I'm like, Tyler. Yeah, so we're kind of stuck with Mr. Colger.
Yeah, that's fine.
But he is a BC teacher, so he matches our curriculum precisely.
Yeah.